the Panama Canal. Considered by many to be the eighth wonder of the world, it cuts through 50 miles of dense tropical jungle and solid rock, and provides a 10-hour shortcut between the Atlantic and Pacific Oceans, versus a treacherous 2-week passage around the tip of South America. Each year, thousands of ships go through the canal and are literally lifted across Panama's mountains by a remarkable series of water elevators and man-made lakes. When the canal was finished in 1914, it was a marvel of engineering, able to handle the mightiest ships of its day. But that time has passed. Today, new supercargo ships are double, even triple the size, putting Panama at a crossroads. Do they gamble billions on redesigning the canal for the 21st century? Or lose billions in revenue from all the ships the canal can't handle? The very future of that country could be riding on that decision. It's 6:30 in the morning at the Atlantic entrance to the Panama Canal. Senior pilot Dave Sherman is about to take control of a Russian-operated oil tanker. The Panama Canal is the only place in the world where a captain must surrender command of his vessel.
Where you guys at?
We're in the swell. We need a 9-meter rig, otherwise someone's gonna get hurt.
After 25 years on the job, Dave still looks at every canal crossing as an adventure and knows he can never let down his guard.
Morning.
Good morning.
How are you?
Welcome on board.
Thank you.
Yeah, please.
Navigating the canal is a high-pressure, highly skilled job from end to end.
Gatun. Good morning. Dave Sherman. How are you?
Dave's now responsible for the ship and its cargo. In every lock, around every bend, danger lurks. Even the smallest mistake could be catastrophic. From the Atlantic side, Dave will have to navigate through 3 locks that will raise the tanker 85 feet to the level of Gatun Lake. At the other end of the lake, another set of locks will lower the ship back down to reach the Pacific. The locks are the key to the canal. But how do you pick up a giant cargo ship or oil tanker? Each lock consists of 3 separate but connected chambers. As the ship enters the first lock chamber, specially trained workers cast ropes to attach 1-inch thick steel cables to the bow and stern of the ship. These are connected to high-powered locomotives that ride along either side of the canal. These locomotives can tow 35 tons. That's like pulling 2 F-14 jet fighters. But it's going to take 6 locomotives to guide this 65,000-ton ship into the lock chamber. Dave slows the engines. It's here in the locks that his piloting skills first come into play. The Russian captain is nervous. His ship is 105 feet wide. Each lock chamber is 110 feet wide. That leaves only 2.5 feet of clearance on either side. By constantly adjusting the tension on the cables, the locomotives keep the ship centered in the lock chamber. Their movement must be perfectly synchronized to keep the cables taut. The doors close, holding back the ocean water. Up in the nearby control tower, operators turn the valves, releasing fresh water from Gatun Lake to raise Dave's ship.
Control house.
These are the same controls that were installed more than 90 years ago. Gravity pulls the water down from the lake and sends it into the lock chamber through 100 man-sized holes in the floor. The rising water begins to lift the ship to the level of the next chamber. The water must fill evenly. Any turbulence could smash the ship against the sides, snapping the taut half-ton steel cables with enough force to slice a person in half. Once the ship has been raised, the locomotives climb to the next elevation. The 750-ton doors slowly swing open. The process is repeated until the ship has reached the level of the lake, 85 feet above the Atlantic. A ship of this size is considered a Panamax ship because it is the maximum size that can fit through the Panama Canal. When the canal first opened in 1914, the size of the locks in Panama actually set the standard for shipbuilders. Today, 13,000 ships per year transit the canal, carrying 190 million tons of cargo, generating almost $600 million in toll fees for the Panamanian government. But the Panama Canal has a problem. The world of commercial shipping is beginning to pass it by, literally. The new supercargo ships are too long and too wide to fit through the canal. But they are a sign of things to come. They are capable of carrying 3 times the cargo and are hundreds of feet longer and wider than the largest ships the canal can handle. Either the Panama Canal grows with the commercial shipping industry, or it will be left behind. These super ships are leading the container and bulk cargo business. Today, they make up 20% of the ships at sea. By the year 2020, that number will at least double. For these megaships, it's as if the Panama Canal was never built. The U.S. began relinquishing control of the canal to Panama in 1979, making this tiny country of only 3 million people a major player in international commerce. And yet, few suspected the true cost. They would soon discover that their golden egg had lost some of its luster. Not only were they losing business to the supercargo ships, but the canal itself had become dangerously run down. Major improvements were needed, and quickly, simply to keep the Panama Canal open.
The Panamanian people play the most important role in our decision making. The canal is extremely important for Panama. So the benefit that any expansion on any program that we put forward has to benefit the people.
Many of the improvements are already underway. 100 more powerful locomotives, each costing $2 million, now guide the ships through the locks. A fleet of stronger, more maneuverable tugs is already escorting vessels, like this 80,000-ton container ship, through the narrowest part of the canal. Communications between ships and canal operators, so vital to safety, have been updated. A global positioning satellite system helps engineers to monitor the movements of many ships in the canal with pinpoint accuracy. And in the near future, an onboard tracking system will become mandatory. But these improvements are the easiest parts of the renovation. Far more difficult ones lie ahead, such as widening the canal where it cuts through Panama's mountainous spine. It is a daunting challenge, both in its scale and in its projected cost, $7 billion. Panamanians could be gambling with the very future of their country. And yet, do they really have a choice? Bulldozers will have to clear-cut thousands of acres of jungle at both ends of the canal. Excavators will need to dig deep into the earth, through thousands of feet of unstable rock and mud. Millions of tons of concrete will have to be poured. But the biggest engineering challenge of all will be building brand new locks next to the current ones. Locks big enough to handle the new megaships. These new locks will need to be 3 times the size of the originals, making them the world's largest.
We are using technology today that back in 1904 didn't exist. And I think that we can solve the engineering problems that we are facing in an engineering way. I think that there are solutions to that.
Yeah, what's the status of Southtown tugboats?
Back on the oil tanker, 2 hours have passed since Dave guided the ship out of the locks and into Gatun Lake. It's a freshwater lake that covers an area 6 times the size of Manhattan. The lake is the great engine that powers the canal. It pumps 55 million gallons of water into the locks to lift and lower each ship through the canal. With up to 40 transits a day, that's 2 billion gallons gone each day that must be replenished. Gatun Lake also provides fresh drinking water for over 1 million Panamanian people. To create the lake, engineers built the Gatun Dam, then the largest in the world, across the Chagres River. It was a remarkable feat of extreme engineering. The lake is replenished by Panama's heavy rains. But there's a problem. Global warming is creating irregular rainy seasons. Low rainfalls cause the water level in the lake to drop, preventing ships from crossing with their full load. They must offload cargo to reduce their draft. Ironically, too much rainfall also causes major problems. Hydraulic engineer Carlos Vargas is responsible for maintaining the canal's water levels.
If we couldn't open the gate and the lakes go too high, the locks itself will be flooded, and the Panama Canal operation will have to be stopped to repair and to release the water, and that causes damage to the clients and to the image of the Panama Canal.
Ideally, the water level on the lake should be 85 feet above sea level. Senor Vargas sees that today the level has climbed to a dangerous 87 feet. He calls for immediate action.
Hola, este es Carlos Vargas, manager de hidrología. IP 2204-428, por favor.
Enormous engines inside the dam wall now lift one of the dam's 52-ton steel gates. Within 5 minutes, 20 million gallons of water surge out into the spillway on their way to the sea. And the water level falls to a safe 85 feet. Meanwhile, the oil tanker has made its way across Gatun Lake and is about to enter one of the most treacherous sections of the canal, the Gaylord Cut. This is the narrowest part of the canal, a twisting, turning channel cut through Panama's mountainous spine. This is where Dave's skills get their toughest tests. These mountains were the reason why the canal project almost never happened. The idea seemed so simple. Just dig a ditch 50 miles long by 500 feet wide, and presto, you've connected the Atlantic and the Pacific. But the mountains of Panama were not conquered so easily. They defeated the first attempt. It was the sunny optimism of the early Industrial Revolution that led the great French businessman Ferdinand de Lesseps to tackle the project in 1873. De Lesseps had just come off another engineering triumph, constructing the Suez Canal in Egypt. There, workers had been able to dig a ditch at sea level through the flat Egyptian desert. But Panama presented far more problems than de Lesseps ever imagined. Not only the mountains, but a living threat as well: malaria and yellow fever. At the time, scientists didn't know that these deadly diseases were carried by mosquitoes. Workers died at an alarming rate. After 10 years, the French had finally had enough. By then, 20,000 men were buried in the jungles of Panama, and de Lesseps' business and reputation lay in ruins. Nature had won the first battle, but the war had just begun. The next visionary to take up the cause of a Panama Canal was a real soldier, Theodore Roosevelt. Roosevelt chose John Stevens, a brilliant railway engineer, as the chief of the Panama Canal project in 1905. Stevens had never built a canal before, but he knew how to think big. The first thing he did was to stop all construction work and focus on the health of the workers. Stevens threw all his resources into eradicating yellow fever and malaria from Panama. It worked. In just a year, the fumigation army had eradicated the diseases. Now Stevens could tackle the engineering problems. First on the list was the treacherous Chagres River, which produced killer floods. Rather than fight the river, as de Lesseps had done, Stevens decided to exploit it. He proposed damming up the river where it flowed to the Atlantic to form a lake, Lake Gatun, 85 feet above the oceans. This old film demonstrates his idea. Stevens designed a set of 3 locks on either side of the lake to lift and lower ships over the mountains to reach sea level on the other side. For their time, Stevens' vision and the lock scale were monumental. No one had ever built locks 1,000 feet long, 110 feet wide by 85 feet deep, with 18-foot diameter water pipes big enough to hold a railroad car. Each swinging lock gate would be 65 feet wide and 7 feet thick. Manufacturing the massive amounts of steel for these gates soon kept every steel mill in America busy. It took 4 years and a workforce of thousands to complete the locks. At the time, it was beyond everyone's wildest imagination that someday these locks would be too small. Meanwhile, armies of men were trying to blast, dig, and shovel a channel through the mountains.
Working through the Gaylord Cutter, constructing the canal was actually an engineer's nightmare. As you can see, the type of material that you have here is very, very bad material. And even during the excavation works, they were creating landslides.
After every landslide, the workers had to dig out. By the time they finished carving out Gaylord Cut, they had enough dirt to fill a trench 55 feet wide and 10 feet deep from San Francisco to New York City. The Panama Canal finally opened in 1914. It had taken 30 years, $400 million, and more than 30,000 lives. It was heralded as a marvel of extreme engineering, a testament to the unlimited potential of human ingenuity.
Connecting these two large oceans is basically almost the same feat as putting maybe a man in the moon, the same target, the same determination.
Few people going through the canal today know the extent of human sacrifice required to build it. Certainly the past is not on Dave's mind as he pilots the oil tanker. He's now halfway through the Gaylord Cut, in the narrowest part of the canal. Any mistake now, even the slightest wrong turn, and you could ram a rock face and crash the ship.
Is this your radio? Can we maybe get rid of that frequency?
Yeah.
But for those without Dave's 25 years of experience, there's a safer way across the canal.
Roger. Slow ahead. Slow ahead.
In a 360-degree pilot simulator, one of only 4 like it in the world. In effect, it is the greatest arcade game of all, giving a pilot in training the full experience of a virtual canal crossing, complete with every nightmare scenario, from thick fog to loss of power, collisions.
Come on, we're heading for the bank. I need you now.
Heavy swells, and 100 more dangers. Right now, pilot Jeffrey Robbins has his hands full. He's guiding a virtual oil tanker through Gaylord Cut.
Amistad, I need you.
And he's just lost an engine.
Come on, get that line up.
He radios the captain of a nearby tug for help. He and his first mate are fighting to keep the ship from grounding on the bank. They could cause a massive landslide, shutting down the canal. Millions of dollars would be lost, and heads would roll.
Okay, Unidad, stop and line up to keep that stern away from the bank. Swing around.
Luckily,
the port.
it's a near miss.
Yeah, everything's okay.
And yet, even the best training for pilots cannot protect vessels or the canal itself from the greatest danger they face: landslides. They occur on the canal on a daily basis. In 1915, just a year after the canal opened, 8 miles of earth along the banks of the Gaylord Cut collapsed into the channel. The danger remains because of the unstable structure of the soil, layers of rock, clay, and shale. Not only are the banks unstable, they also slope at an angle towards the canal. When it rains, water soaks into the porous layers, adding tremendous weight to the banks. Then, gravity does the rest. It is an endless problem. Every day, all year round, dredges scoop out what has slid back in. They've been at it ever since excavations first began on the canal in the 1880s. Today, state-of-the-art dredgers like this one can haul 125 tons of mud and rock in a single scoop. On any given day, they dig up enough mud to fill 170 Olympic-sized swimming pools. If engineers start widening and straightening the canal for the megaships, they'll have to dredge out enough mud to fill up millions of swimming pools.
I think that the earth moving, which is the name of the game here, is going to be key. As the ships get larger and the draft gets deeper, dredging will be required to be more precise, and the demands on the production will be greater.
But dredging alone won't be enough to widen and deepen the canal. They will also have to blast, which raises the risk of even more serious landslides. But engineers have no alternatives, so it's a risk they'll have to live with. Dave's oil tanker has made it safely through the Gaylord Cut. He must still navigate the Pedro Miguel locks, which will lower him 31 feet to Miraflores, another man-made lake. The proposed new locks will be built right next to the old ones. Smaller ships will continue to use these old locks, while in the future, mega ships will use the new ones. Construction of these new locks is the greatest challenge facing engineers. To find the best possible design, Panama has created an engineering competition rivaled only by the contest to rebuild the World Trade Center site. Two design teams have emerged. An American team will create a design for the canal's Atlantic locks, and a European team will conceive the locks for the Pacific end. The American team is the canal's original builders, the U.S. Army Corps of Engineers. They're excited to do it all over again.
If you're a civil engineer and you love big projects, it just doesn't get any better than working on the Panama Canal.
For the 85 years that America controlled the canal, Panama's geology was always the biggest headache. And geology is going to determine how the Corps builds the Atlantic locks.
The Atlantic side has the softer rock. Pacific side has very hard rock, and that means that makes a lot of difference in the type of structure that you design.
To construct new locks in the soft, unstable rock, the Corps is looking at new technologies. Now in use on the Ohio River in Olmsted, Kentucky. For 5 years, engineers struggled to design a new lock and dam here on one of America's busiest waterways. If they had shut down the locks while they built the new dam, they would have cost the U.S. $2 million a day. So engineers had to find a way to build a new dam without closing the waterway. They went back to the drawing board and finally came up with a radical proposal: to construct the dam in the wet.
Trying to eliminate use of cofferdam.
Instead of building a massive dry construction site in the middle of the river, they prefabricated sections of the giant structure on land, then floated them out into the river, where the buoyancy made them 10 times lighter. Then they assembled them like Lincoln logs. The same method could be used to build the Panama Canal's new Atlantic locks. But the canal's new Pacific locks face a different problem. Powerful ocean tides. Twice a day, the tides at the canal's Pacific entrance rise and fall 22 feet, putting enormous pressure on the gates of the locks here. To cope with this pressure, the engineers had to build gates that are the tallest and strongest on the canal. But the gates for the new Pacific locks must be almost twice as big, nearly as tall as a 10-story building.
Well, I think that's the most difficult thing, in my opinion, is the lock gates, because they are quite complicated steel structures.
Jose Regue and his team decided that they could come up with a better design than the type of gates now in place on the canal. That type of gate works like French doors that swing open and closed. Instead, Regue chose a design that's in use today in Antwerp, Belgium, in what are currently the world's largest locks. They're known as rolling gates because they roll into place across the lock chamber from a pocket in the lock wall. Only inside do you get a sense of what a monster this Belgian gate is. 2/3 as long as a football field, 7 stories high, and 60 feet wide. It makes Panama's lock gates look like the doors of a dollhouse. In dry dock, this gate weighs 1,500 tons, as much as 5 Boeing 747s. But as heavy as each of these gates is, it would be just half the weight of the proposed new Panama rolling gates. How will engineers roll a 3,000-ton gate across the 200-foot wide lock? They won't have to. As this model shows, the buoyancy of the water reduces the effective weight of the hollow gates to a mere 100 tons. But before any designs can be approved, they must be tested using scale models in labs like this one in Mississippi, run by the Army Corps of Engineers.
Working here at the Corps' research lab has really been enjoyable for me. Oftentimes we have been accused of being big boys with big toys, when it really is a lot of fun, especially when we see something that we help design and make a lot better.
Engineers test how well the new locks will fill up and empty under heavy water pressure. The new lock design must allow water to rise evenly and calmly, or the results could be catastrophic for a real ship. The threat of an accident is never far from the minds of the canal's engineers and pilots like Dave Sherman. He's about to guide the tanker through the final set of locks near the canal's Pacific entrance. The canal crossing has cost the tanker's owner $295,000 in tolls. But that's a whole lot cheaper and safer than taking the long way round. But before engineers build a shortcut for the new megaships, they're going to have to solve one more problem. This one could be the killer. What will power the locks? Water is the engine that drives every lock system. But Gatun Lake doesn't hold enough water to lift the megaships through the new locks. Engineers must solve the water problem, or their dreams of enlarging the canal for the new super cargo ships will die. They are exploring 3 options. One is to reduce the number of chambers in the lock from 3 to 2. Fewer chambers will save water, But one less chamber also puts the drinking water of millions of Panamanians at risk. That's because currently, salt water entering the lock chamber closest to the ocean gets diluted by fresh water in 2 more chambers. Removing one chamber means that more salt water may enter the lake. But there's another possible way to solve the water problem. Create a new lake by building another dam on a nearby river. But damming the river would mean flooding thousands of homes. And that's too high a price for the Panamanian government. Luckily, there's a third option, currently in use in Germany. It's called a ship lift. Instead of raising the water level in the lock chamber to raise or lower a boat, they actually lower or raise the lock chamber itself. After a boat enters the chamber, gates on both ends are closed off, so the boat is now in effect floating in a bathtub. The chamber is then raised or lowered to the next water elevation. The gate at one end opens, and the boat continues its journey. The best part is that no water is wasted. But these boats weigh 1,000 tons, a mere 1/60th of the ships in the Panama Canal. Engineering a lift mechanism strong enough to lift one of these ships would be beyond extreme. But there is another method of using water in the locks that may turn out to be the answer. A system of holding tanks that recycles water. When a ship wants to transit from a higher elevation to a lower one on this German canal, engineers release water from the top lock chamber. But instead of just spilling out into the river, the water flows into a nearby holding tank. Then, when another barge needs to be raised to a higher level, engineers can use the recycled water in the holding tanks. If engineers can build a similar set of holding tanks for Panama's new locks, they might be able to lift and lower the new megaships with just the same amount of water that's now used in the old locks. But even if engineers can solve the problem of water power, they must still confront a terrifying natural threat that could overwhelm all their efforts. Earthquakes. Panama has recently been experiencing an increasing number of tiny earthquakes. Earthquakes occur when geological plates grind against each other. Panama lies dangerously close to 4 of these massive plates, but has not been hit by a major quake since 1882. The new increase in seismic activity could actually be a good thing. Evidence that the plates are safely releasing built-up pressure. But these little tremors may also be the first warnings of a killer quake to come. The most dangerous effect of any quake would be to damage the Gatun Dam. If the dam cracked open, the lake would be bone dry in 6 days, and the canal would be out of commission for 3 years. That's how long it would take for rainfall to refill the lake. But Gatun Dam's walls are 400 feet thick, and even the most pessimistic forecasts don't anticipate a quake strong enough to crack them. Even so, both design teams are working to minimize a quake's impact on the new locks.
If you should ever have an earthquake and the structure has not been designed for it, taking into account the high water pressures and the high water heads, it would be a disaster if anything happens with the locks.
Engineers recognize that any structure subjected to a major earthquake will suffer some damage. But their goal is to prevent a complete collapse. Could the new giant locks survive a killer quake? a possible disaster scenario might look like this. The year is 2030. The world's biggest locks are up and running. Operators in the control tower carefully monitor the locations of all 68 ships in the canal. A super cargo ship has just sailed into the last of the 3 new locks on the Atlantic side. When suddenly it hits. A devastating earthquake measuring 8.6 on the Richter scale. 100-ton cargo crates are thrown about like Lego blocks.
Call the Emergency Operations Center.
Hello, ma'am, please.
Clear the lock.
Operations Center.
Engineers immediately shut off the flow of water into the locks. 30 heart-stopping seconds later, it's over. The locks have sustained some damage, but they still work. Canal engineers have triumphed over the worst that Mother Nature can throw at them. At least that's what they hope will happen. But no one can know for sure until the canal has actually been rebuilt. It's 6 p.m. as Dave Sherman steers the oil tanker out of the last set of locks and into the Pacific Ocean. It's taken 10 hours, but his job is now done. One day in the near future, Dave could be piloting a ship twice, even 3 times the size, through a wider, deeper canal. But enlarging the canal presents challenges that outstrip even the terrible problems that plagued its original construction 100 years ago. Certainly the project is a huge gamble, but the winnings could be extraordinary. A bigger canal would catapult Panama back onto the world stage as one of the real power brokers of international commerce. The entire world awaits a new Panama Canal. When the first supercargo ship steers into the first new lock, it will change the way we travel and the way we do business, just as the original Panama Canal, when it connected the Atlantic and Pacific Oceans, changed the very face of the world.